I will start by exercise 1. In the copper atom Cu2963, we have several possibilities A, B, C, D, and E. I told you about 3 types of questions. The first type of question is the application of the knowledge. That means you should not do calculations. You have to know the concept and to answer directly. The second types of exercises in the multiple choices is the elimination by thinking. What is the meaning? Some of the answers, for example, can be eliminated directly. So our choice will be, for example, if we eliminate in this exercise C, D, and E directly, so our choice will be between A and B. So it makes easier the reading of the exercise. And the third type is the method and calculation. You have to do calculations in order to find the answer. So in the copper atom 6329Cu, this is a question of the application of knowledge. For element representing by XAZ, X is the symbol of the element, A is the mass number, and Z is the atomic number, which is the number of protons. So in this exercise, we have 29 protons, and since the atom is neutral, the number of protons is equal to the number of electrons, so we have 29 electrons. A is the mass number 63, and N is the number of neutrons, which is equal to A minus Z. So 63 minus 29 equal 34. So we have 29 protons, 29 electrons, 34 neutrons, and 63 the nucleons, which is A, which is the proton and the neutrons. So the answer is E, B and D. 63 nucleons, 29, this is true. And D, 34 neutrons, 63 nucleons, and 29. So the answer is B and D. So the answer is the part E. We pass to exercise 2. Which of the following are isotopes? This is the carbon, nitrogen, carbon, silicon, nitrogen 14 and nitrogen 15, or the answer is B and D. What is the definition of isotopes? Isotopes are different atoms of the same element, but they have the same Z, since we have the same element, and the difference is in the mass number A. So they have different number of neutrons. Isotopes are different atoms of the same element, of same Z, different A, so of different number of neutrons. Carbon 14 and carbon 14 are atoms of the same element with the same A. So A is incorrect. B, carbon 14 and nitrogen, for example, 14, we don't, okay, is incorrect because we have atoms of different elements. C is incorrect. The correct answer is D. We have N, so atoms of the same element, and the difference is in the mass number A, which is equal to 14 in the first and 15 in the second. So the answer is D. Exercise 3. What is the energy of photon of light that has lambda equal 6 times 10 to the power 2 nanometer? We have a relation between the energy of the photon, the frequency of the photon, of the radiation of light, and the wavelengths of the radiation, E equal h nu equal hc over lambda. We have to pay attention how to use these terms. E, h, c, and lambda should be in the same system, the SI system, the international system. So A is in joule per second, C in meter per second, lambda in meter, and E in joules. So E equal 6.62 times 10 minus 34. C is equal to 310 to the power 8 divided by lambda. Lambda given is in nanometer. It should be transformed to meter. 1 nanometer equal 10 minus 9 meters. So E equal 3.3 times 10 minus 19 joule, and the answer is B. To note that H, C are given in the exercise, and the conversion from nanometer to meter is also given. We pass to exercise 4. The blue color in fireworks is obtained by heating copper chloride, CuCl, to about 1200 degrees Celsius. Then the compound emits blue light having energy 4.41 10 minus 19 joule. What is lambda? This is the inverse of exercise 3. First, the data given is a direct application about Planck theory. When a metal is heated at certain temperature, it will emit light. So E absorbed equal E released equal h nu equal hc over lambda. So what is the wavelengths? We apply also the same relation, E equal hc over lambda. So lambda equal hc divided by the energy of the radiation. Lambda equal 6.62 10 minus 34. C is 310 to the power 8, and the energy should be used in the international system joule. So we obtain lambda in the international system unit, so lambda is in meter, equal 4.5 10 minus 7 meter. The answers proposed are in nanometers, so we have to multiply the by 10 to the power 9, so equal 4.5 10 minus 7 times 10 to the power 9, so equal 4.5 times 10 to the power 2 nanometer, so equal 450 nanometer, and the answer is B. We pass to exercise 5. When light having lambda of 497 nanometer, and this radiation strikes a metal, an electron with kinetic energy 2.52 times 10 minus 19 joule is ejected. So what is the threshold frequency for this metal? This exercise is an application of the photoelectric effect. And the photoelectric effect concept, when a radiation of energy E strikes a metal of binding energy E0 or of threshold energy E0, we will have electron ejected from the surface of the metal, and this electron has a kinetic energy. The principle of conservation of energy, E total, that means E of the radiation, initial radiation, equal E0 plus Ek, which is the kinetic energy of the electron ejected. So in this exercise, we have to apply only the formula E total equal E0 plus Ek. E total is the energy of the radiation that strike the metal. And we can calculate E total since we have lambda of the radiation. E0 is the binding energy of the metal or the threshold energy. So this is the unknown. And from E0, we can calculate the threshold frequency mu0. Ek is the kinetic energy, which is given. So E0 equal E total of the radiation minus kinetic energy of the electron ejected. E0 equal h nu 0 and E initial of the radiation equal hc over lambda of the initial radiation minus Ek. This is the relation that should be used. The most important is to pay attention that all terms in this equation should be used in the same system, the SI system. So mu0 equal hc over lambda minus Ek divided by h. Mu0 equal 6.62 10 minus 34 times c 310 to the power 8 meter per second divided by lambda in meter. So we have to transform 497 times 10 minus 9 meter minus Ek in joule, which is given 2.52 10 minus 19, and divided by h, which is the Planck constant in joule per second. So the mu0 obtained in this case should be in second minus 1 or in hertz, which is equal to 2.23 times 10 to the power 14. So the correct answer is D. We pass to exercise 6. What is the binding energy or work function? I prefer to use the bind energy in joule per mole. Pay attention, underlined, joule per mole of an electron in a metal where the threshold frequency for the photoelectrons is 2.50 times 10 to the power 14 second minus 1. What is the trick in this exercise? In the photoelectric effect, when the radiation strikes a metal, we have electron ejected. And the electron ejected has a certain energy. So the kinetic energy of the electron ejected is electron per 1 electron, is joule per 1 electron. And he asked us to calculate the binding energy in joule per mole electron ejected. So we have difference between joule per 1 electron and joule per mole of electrons. And to remember that when we transform the microscopic scale to the macroscopic scale, we divide it by the Avogadro's number, and when we transform from the macroscopic scale to the microscopic scale, we multiply by Avogadro's number. So for one electron, which is in the microscopic scale, the binding energy E0 is equal to H nu 0. So E0 equal 6.62 10 minus 34. We put mu 0 by its value, so we obtain E0 per 1 electron. For 1 mole of electron, we have to multiply by Avogadro's number because this is at the macroscopic scale. So the energy binding for 1 mole of electron is equal the binding energy for 1 electron times Na. 6.023 times 10 to the power 23. So the answer is 99700 joule per mole of electrons and equal 99.7 kilojoule per mole. We multiply by 10 minus 3 to transform joule to kilojoule. So the answer is A.